first of several promised videos on the topic of Newton's law of cooling in this case. Some more exponential growth and decay stuff. So Newton's law of cooling is this fancy looking equation here. Believe it or not, it is still a form of y equals ce to the kt. There's a couple of small differences. One is this plus c at the beginning. That's actually the simplest difference. This plus c, that just moves your horizontal asymptote up and down. It's just an intuitive vertical shift, just moves everything up and down. The rest of this is a little bit weird, and I want to mention briefly why it's so weird. And the reason why has to go with the nature of temperature itself. See, temperature is this odd thing we've come up with. I know you're going to say we didn't come up with it, but we kind of did. See, in the early days, it was very hard to figure out how warm or cold something was because it was pretty subjective. Those of you in my classroom in the afternoon know that no two people can agree on whether it's too warm or, once the air conditioning kicks in, whether it's too cold. There's an old thought experiment going back hundreds of years before people had decided on a temperature scale, which said if you're standing in a comfortable room and there's two buckets of water, one of which has really warm water, another which has really cold water, and you put a hand in each bucket. Well, after a few minutes, that's going to get really uncomfortable, but then you pull your hands out. And the hand that was in the cold water, that hand feels really warm in the normal, comfortable air. The hand that was in the really warm water, that hand feels really cold in the normal, comfortable room temperature air. So most of your body just feels fine, just sitting there, feels very comfortable. So if somebody asks you in that moment, though, what the temperature is, you've got one hand that feels cold, one hand that feels warm, and most of you feels fine. So how warm or cold is it? Well, eventually, they had the idea to stop making it so subjective and to tie temperature to physical phenomenon. For example, the freezing point of water and the boiling point of water. Now, one bit of historical trivia I don't know is under what numerical system 32 became the freezing point of water and 212 became the boiling point of water. I'm sure it made sense to somebody at some point, but that's Fahrenheit, and that's what we use here in America for whatever reason. Most of the rest of the world uses the metric system, which places 100 degrees Celsius as the boiling point of water and 0 degrees Celsius as the freezing point of water. Now, there's a fundamental problem with both of these scales in that they don't represent actual heat energy. From a physics, chemistry perspective, they're both very problematic. Those of you who've taken chemistry might already know this. But 32 degrees, ice is freezing. Water's freezing into ice, it's very cold. But 64 degrees is not double the heat energy of the freezing point of water. And 96 degrees is not triple that heat energy at all. That's not even possible if you start with 0. You can't double or triple 0 and have any meaningful expression that describes how warm something is. Because the problem is, when water freezes isn't the absence of heat. As far as the universe is concerned, frozen water on Earth is still actually pretty warm, which is why those of you in chemistry have already studied the Kelvin scale. And the Kelvin scale is a scale that is designed to actually preserve ratios and percent changes in heat. So 0 degrees Kelvin down here in the negative 400 degrees Fahrenheit, 0 degrees Kelvin is the theoretical cold at which all molecular action stops. It's not just the absence of heat, it's basically the absence of energy of any kind. And on the Kelvin scale, if you get up here if you start moving up the Kelvin scale, percentages are preserved. So 100 degrees Kelvin is half of 200 degrees Kelvin. And if you go up to 400 degrees Kelvin, that's double 200 degrees Kelvin, because the Kelvin scale is actually supposed to measure heat, which is slightly different from temperature. Temperature is a way to describe how much heat something has. But the problem is, as far as the universe is concerned, there really isn't cold, there's just the absence of heat. compared to outer space, 32 degrees is actually pretty toasty. And you can see that because when here, if this were an actual numerical scale that represented heat energy, going from the freezing point of water to the boiling point of water, 32 to 212, would represent a 562.5% increase. Okay? On Celsius, starting at 0 and going to 100, starting with nothing, 0 meaning nothing, going to 100, that's an infinite percent increase. That's not a thing in math. That doesn't happen. But the actual heat energy jump from the freezing point of water to the boiling point of water on the Kelvin scale is a 37% increase because it takes 37% more heat to take ice and turn it into steam on a scale that starts with the complete absence of heat. So the Kelvin scale might just be a good thing to use when talking about heat, but we don't. And Isaac Newton actually came up with a way around this problem that involved temperature not really representing heat. And that was his law of cooling, where this C, okay, is the constant temperature of the surrounding medium. What that means is the temperature of the room, or more specifically the air in the room. So a lot of these problems will involve taking something out of a freezer, for example, or out of an oven, and then having it slowly thaw or cool or warm itself to the temperature of the surrounding air in the room. And the other way he got around this whole temperature, percent change in heat energy thing, is he didn't talk about a particular scale, but this part, this T initial minus C, that's comparable to the initial amount in most exponential growth and decay. And what that actually describes is the difference between the object and the room temperature. But the important part is it's the initial difference. Right when you bring the hot object out of the oven, okay, what's the difference in temperature between that object and the air of the room, the air of the kitchen? Okay, right when you bring an object out of the freezer, what's the difference in temperature between the frozen object and the air? And that's what this models almost perfectly. And I say almost perfectly because no exponential growth and decay model works perfectly forever. Here we have something that starts at 210 degrees, something you've just taken out of an oven maybe, in a room that is 70 degrees, okay? And what happens is, basically the 210 degree object, its temperature decays slowly to a temperature of 70 degrees. Now this model, as you know, doesn't represent this object ever getting to a temperature of 70 degrees. It's the whole thing about asymptotes, you never reach them. In real life, there is some point where this model fails and the asymptote is reached. But that's because these mathematical models, well, as I've said before, they work until they don't. And then the object is just sitting there at 70 degrees. But it's a great start. And it's brilliant of Isaac Newton to use this initial difference of temperatures as an initial amount and to use the room temperature as of a horizontal asymptote. Nearly perfect model. Guy was really smart. Okay, so let's do an actual problem so that you guys can see how this works. A cake removed from the oven has a temperature of 210 degrees Fahrenheit. It is left to cool in a room that has a temperature of 70 degrees Fahrenheit. After 30 minutes, the temperature of the cake is 140 degrees Fahrenheit. Now, Newton's law of cooling is the temperature of the object equals the room temperature plus the difference between the initial temperature of the object and the room temperature, e to the kt. And as usual, the problem is finding k. That's always the tricky part. And I can give you a formula like I did for CE to the KT, but I think in this case it might be a little better to just muscle it out. So we're going to plug in all the information they gave us. They gave us the initial temperature of the cake was 210 degrees. They gave us the temperature of the room is 70 degrees, and they said when T equals 30, the temperature of the cake had gone down to 140 degrees. So I'm going to plug all that in to Newton's law of cooling up here, and let's see what we get. Because what we're doing is solving part A, find a model. And to find a model, we have to find K from this other information they've given us. Okay, so I'm going to go ahead and start plugging in that the cake was 140 degrees down from 210, but 140 degrees put in a 70-degree room, plus we have to find the difference between the original temperature of the cake and the 70-degree room, and that's our coefficient in front of E raised to the K, but in this case, instead of T, we're going to write 30 because they gave us this initial information, and I'm plugging that in to solve for my K value. Okay, so now from here it's algebra and maybe some logarithms. The 140, oh, no, I'm not going to write that because my very first step is going to be to subtract 70 from both sides. 140 minus 70 is 70. I'm going to go ahead and work out the 210 minus 70, which is 140. And that is still my coefficient before the E raised to the K. The time is still 30 in this case. So now I divide both sides by 140 here. And that gives me 70 over 140 equals E to the K times 30. Then take the natural logarithm of both sides. Natural logarithm of 70 over 140 equals natural log of E to the K times 30. I'm going to whoosh down the K times 30, make it a coefficient, as we've done before. I'm going to simplify the natural log of 70 over 40 to 1/2. So that's going to give me 30 times K times the ln of E. I'm going to remember that the natural log of E is 1, so I can ignore that. I want to mention something real quick about this 1/2. Total coincidence. Total coincidence for this problem. This is 1/2. It's got nothing to do with half-life or any of the other Easter egg shortcuts I told you about half-life. Do not assume that Newton's law of cooling will consistently or even ever again give you a 1/2 inside this natural logarithm over here. So now back to our problem. K is going to wind up being the natural log of 1/2, again a coincidence in this case, divided by 30. So solving K is important, but that's not what the problem said. The problem said to just find a model, which we're going to do in a sec here. Going to erase the rest. I'm going to leave that K there to make sure I don't forget it. And my model is that the temperature in general is equal to 70, the temperature of the room, plus 140, that hasn't changed, E raised to the natural log of 1/2 over 30 times T. That is my actual answer for A. This is the point where I would say, are there any questions? But I guess you'll just have to email me those, and I'm going to roll right into part B. Okay. What is the temperature of the cake after 40 minutes? Cool. Well, we got our model here, which honestly I should have kept, but easy enough to copy. And mostly easy enough to copy. All right, wait, there it went. There we go. Okay, so this is just a matter of plugging 40 into my model. So I'm going to write that T is 70 plus 140E raised to the natural log of 1/2 over 30 times 40 minutes. I don't know what this is off the top of my head, but let's find out. I've got an old calculation sitting here. So how's my memory? Okay, there we go. What I want to calculate is 70 plus 140e raised to the natural log of 1/2 over 30 times 40. Yes, I could have simplified this, but I'm going to go ahead and I like seeing it all spelled out. You guys know that about me by now. Okay, so 70 plus 140. Cool. It's kind of a pain to put this picture into my PowerPoint from the iPad, so I'm just going to remember that. And that is 125.559. Okay, let's go on to part C. Again, sorry I'm not stopping for any questions, but, and once again, deleted my model there, but let's see if I can remember it. T equals 70 plus 140e to the natural log of 1/2 over 30t. Okay, but now what the question we're answering is, when will the temperature of the cake be 90 degrees Fahrenheit? Okay, so now we're going to plug in 90 degrees for the temperature, and we're going to solve for time. So first thing I'm going to do is subtract 70 from both sides. So that's 20 equals 70 plus 140 e to the natural log of 1/2 over 30t. Now I'm going to subtract, nope, I already did that. Sorry about that. Okay, got a little distracted there. I don't know if you guys heard the dog barking in the background. But now, there we go. Okay, so now what I'm actually going to do is divide both sides by 140. And 20 divided by 140 will give me 1/7, which equals e to the natural log of 1/2 over 30t. Now I take the natural log of both sides, and that just gets rid of the e as we saw before. And I'm looking at this equation. I'm going to multiply both sides by the reciprocal of this fraction. So what that will give me over on this side is 30 times the natural log of 1/7 divided by the natural log of 1/2. And that equals t. Now, one thing you may start thinking of here is, what logarithmic shortcuts can I use to simplify this? And the answer is none. Yes, division inside a logarithm does become subtraction, but that's division inside the logarithm. Division between two logarithms, there is no shortcut for that, none whatsoever. So we cannot use this shortcut here. It can't help us. We're just going to have to go straight to technology at this point and put this rule over here, but remember, we're not using it. But you'll get tempted. Sometimes in these equations, you think you see something helpful, but you have to be careful to remember that the rules for operations within logarithms, for expanding or condensing them, they don't apply between logarithms. Okay? But what we can do is go back over here, and we can write 30 natural log of 1/7 divided by natural log of 1/2, and let's see, there we go, 84.220, and let's see, okay, so that is 84 0.220, and this was minutes. Does that make sense? Well, sure. After all, after 40 minutes, the cake had gone down to 125.559 degrees. So getting to the lower temperature of 90 degrees, taking twice as long, that makes sense. But we don't just have to trust it. We can double check with Desmos because I got all my numbers specifically for this Desmos example from this example from your book. And let's see. After 40 minutes, 125.559, that is the answer we got. And 90 degrees, we said was around 84 minutes. Well, let's see, if I go out here to 84.2 minutes, yep, you know what, I'm going to say that's close enough. At 84 minutes, 90, so I'm not going to get this thing to line up perfectly with 90, but we'll just call 84 minutes, 90 degrees close enough. So I'm confident in this answer, and that is how you solve Newton's law of cooling problems. There'll be some homework on the school portal, and I look forward to you emailing me questions, and we can set up individual Zoom conferences if that helps. Hope this was clear, and I look forward to seeing how you do with Newton's law of cooling next time we all meet. Thanks, guys.